Okay guys, this is my second video, so I'm experimenting with the volume, so I'm speaking a little bit louder. We'll see. Board problem 23. Okay, we got parallel box plots of gas mileages for three makes of cars. Which of the followings are true? So number one, all three have the same range. Okay, your ranges are the ends of the whiskers, you guys. So from this whisker all the way out to this whisker right here. So all of these have the same spread from whisker to whisker. So they do have the same range. Part two says all three have the same quartile. Um, well, the quartiles are the box spreads. So they're not, it's not two because this quartile, the inner quartile range, here's quartile 3 where my cursor is. Here's quartile 1. Quartile 3 minus quartile 1 is your IQR, your interquartile range. So they're not the same. This quartile range is smaller than the top one, and this quartile range is bigger than probably both of them, so it's not 2. And then number 3 says the difference in the medians between the first and third quartile, the first and third distribution. So the first and third distribution, the difference between the medians, that's the center line. So that's the median. This is the median here. Over here's the median right here. So is equal to the IQR of the second distribution. Okay, so here's the median of the top one. Here's the median of the second one, and they end up right here, so it is the IQR of that. So it looks like 1 and 3 are true, so I get choice B on that. Okay, choice B. Okay, and there's the explanation I have right there. I'll move along. Okay, so this is section 4.3-2, conditional distributions and Simpson's paradox. We discussed this on our first day of school, Simpson's paradox. We'll get to that. That's at the end of the lesson. Okay, so conditional distribution refers to parts of the data that satisfies certain conditions. So we're going to use the data that we did yesterday on education level and the age categories. Remember that big graph you guys copied down? Okay, so on 4.3-1, that video, all that information comes out of that. So for example, here's an example of a conditional distribution. Find the conditional distribution of education for those in the 25 to 34 years range. Okay, so we got this data from the other video, 4.3-1. So we have age, education, the people who didn't finish homework, people who did, and 1 to 3 years of college, and greater than or equal to 4 years of college. Okay, and this is just for the 25 to 34. Okay, so can you see where we got those numbers right there on the chart from yesterday? So of course divide and get a percentage, and later we're going to be making bar graphs of this information. So this is just the 25 to 34 category, and 1 to 3 years of college. So partial divided by total, and we get that right there. Okay, so that's the conditional distribution from the 25 to 34 years of age of college for their education levels. Okay, so here's section B. Do the same for 35 to 54. Okay, so here we go. 35 to 54. You should get those answers right there. Okay, probably pause and right here, you guys. Well, you probably paused already, and make sure that you get those same answers right there. Okay, and then you're going to do the same for 55 and older. Okay, so go ahead and set up that chart like you see above, and then probably pause it and see if you can get these answers. Okay, make sure you can get those answers correctly. And then, of course, it's going to ask you after you got these numbers. Okay, make sure you got them all. And then you're going to draw a bar graph of these conditional distributions. Okay, of each one, you're going to draw a bar graph. Fortunately, I have pictures of these so I can save some time on this, you guys. Here we go. So this is on page 428. I'm sorry, that's not, it's just figure 4.27, you guys, and it's on page 248. Okay, so scratch this guy out right here. You don't need to worry about that. Okay, so just figure 4.27. Okay, so here's all those distributions that we did. So here's 25 to 34, 35 to 54, and 55 and older. And those are the people who did not finish high school. And then here's the people over here who did finish high school. Here's the people over here that have 1 to 3 years of college. Notice the age group down here and the people in each category. Here's the ones that have 4 or more years of college. Hopefully that'll be you in this category, and that would be you would be probably in this bar. Some people are in this bar. Some people have babies and they don't start education till later. Okay? All right, so there's the bar graphs right there. Okay, Simpson's paradox. Okay, we did a Simpson's paradox.
The Del
We got an
Campo
announcement.
Learning Team is meeting in room 19 right now. The Del Campo Learning Team
That's
in
me.
room 19.
I'm almost done. Okay, so Simpson's paradox refers to reversing the data by either some lurking variables or reversing the relationships between two categorical variables. Usually they're lurking variables, and here's a quick example, okay? Patient outcomes in hospitals. See example 4.23, which is on page 249. I'll read this here. So to help consumers make informed decisions about health care, the government released data about patient outcomes in hospitals. You want to compare Hospital A and Hospital B, which serve your community. Here is a two-way table of data of the survival of patients after surgery in these two hospitals. All of these patients undergo surgery on a recent time period are included. Survived means that the patient lived at least 6 weeks following surgery. Okay, so there's the data on that. And then so we're going to calculate the percentages on this, you guys. The evidence, when you calculate the percentages, is pretty clear, you guys. Hospital A loses 3%, which is 63 divided by the total, 2,100 of its surgery patients. And Hospital B only loses 2%. So it seems you should choose Hospital B if you need surgery, right? But there's some lurking variables hiding, and here they are, you guys. So lurking variables, not all cases are equally as serious, and patients are classified as being either in good condition or poor condition. Here's the data broken down by patient conditions. So here they are. Okay, so these are versus good and poor conditions for Hospital A. So these are a good condition, so 6 died and 594 survived. Hospital B, 8 died out of 592 survived. And over here, poor condition, 57 over 143. I'm sorry, 57 and 1443 and so on. Okay, so when you check that data out, Hospital A beats Hospital B for patients in good condition. Only 1% died in Hospital A compared with 1.3% in Hospital B. And then again, in poor condition, Hospital A wins again. They only lost 3.8% while Hospital B lost 4%. So Hospital A is a safer for both patients in good condition and in patients that are in poor condition, okay? And probably Hospital A had more people that were in poor condition, and that's what the lurking variable was. All right, and that's the end of this video, and I'll see you in the next one. Hope this one worked out okay.